Okay, so here we have some additional gas laws topics. Not on the regents, but not necessarily super hard. We have Dalton's law of partial pressures. So Dalton's law says in a mixture of gases, the total pressure of the mixture is equal to the sum of the pressure that each gas would exert by itself. So each individual gas pressure is called a partial pressure. So I really like this diagram. It shows the total pressure of the mixture at 101.3, which we should identify as kilopascals. So all of the different components of air, oxygen, nitrogen, argon, water, carbon dioxide, they all have their each individual partial pressure. And if you add those all together, you will end up getting 101.3 kilopascal. So if there was a regents question, it would say something like, if we had all of these partial pressures, it'll say, what is the partial pressure of argon? And you would just have to do some subtraction. Very straightforward. So each individual component of the mixture has a partial pressure, which would add up to the total pressure. That's Dalton's law. Diffusion should be a concept that you've learned before. Molecules moving from lower concentration and from high to low concentration until the concentration is the same throughout. So this is obviously not gases. This is probably a lab that you've done in middle school or at least in an earlier science class, where we have a semi-permeable membrane and we have a mixture. This is usually glucose and water. And notice that over time, the particles of glucose are able to distribute until we have homogeneity. We have the same throughout. So that's diffusion. Graham's law of diffusion says, under the same conditions of temperature and pressure, gases will diffuse at a rate inversely proportional to the square roots of their densities. Denser gases will diffuse more slowly than less dense gases. I think that makes sense. It's kind of like, who's going to win the race? The really quick, light person or the heavy, slow person. So you want that light person's going to get there faster. This is the formula. It looks scary, but it really isn't. So V is not volume. This is lowercase v, and it stands for the rate of diffusion. And M, lowercase m, is not mass, it's molar mass. And we're going to do the heavier on top. So M2 is always heavier, and then M1 is the lighter. And you're going to get a whole number, and it's going to talk to you about, which one is going to diffuse faster. And it's always important to talk about it in the correct, relation. So here we have and by the way, this formula is not on the reference table. It's not on the regents. If I were to give it to you in a test, I'd have to provide it to you. Calculate the relative rates of diffusion of oxygen O2 to hydrogen H2. So first of all, the formula is square root of molar mass heavy over molar mass light. So we're talking about who is heavier. Well, we'd go to periodic table. Let's do that. Periodic table. Okay. Well, we're sideways. But here we have oxygen, 15.9994, which is 16, but it's O2, so we've got 1632 grams per mole. Well, that's molar mass, or we could say AMU. And then here we have hydrogen, which is 1, rounded to be 1, and then times 2 would be 2. So we have 32 for oxygen and 2 for hydrogen. So if we go back to this, yeah, I did. So we have square root of oxygen over hydrogen, which is the square root of 16, which means that's a 4. Now what the heck do you do with this 4? This means hydrogen diffuses 4 times faster than oxygen. You could also say oxygen diffuses 4 times slower than hydrogen. And that's because heavier ones diffuse slower anyways, so just take that number and then plug it in. Now, if you got decimals, that'd be fine. You would just, you could round it or just use a decimal. Ideal gas law, also not on the region, so it's an honors situation. Our formula is PV equals nRT, where P is pressure, V is volume, N is moles, and T is temperature in Kelvin. Has to be Kelvin because absolute scale. So what is R? R is a constant. So R is 2 values. It can either be 8.31 kilopascal times liters over moles times Kelvin, or it could be 0.0821 atmosphere liters mole Kelvin. So it really depends on how we measure our pressure as to which R value to use. If you have torr or millimeters of mercury, you're going to have to convert to one of the other ones in order to use that. And it doesn't matter which. I know chemists prefer one and physicists prefer another, but it doesn't really matter. These values are on the honors reference table. So here we have universal gas constant, R. We have this and this. Now, there's also calories, but we don't use calories. We've been using joules. So here we have the liters atmosphere, and this one is the kilopascal. So those are available. I would not be using this because we're using joules for our heat. Joules for heat. So they are there. So back to here. The formula is not that hard, though. Take a look at it. Multiply. It's just multiplying. A gas has a volume of 31.2 liters at a temperature of 28 degrees Celsius and a pressure of 82.6 kilopascal. Assuming it's an ideal gas, how many moles are in the sample? So we have PV equals nRT. So our pressure is given in kilopascals, which means we're going to need to remember that for our R value. Our volume is 31.2 liters. We're looking for moles, that's N. Our R value, remember if it's the kilopascal, that's 8.31, and all those units, blah, 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 kilopascal, liters over moles Kelvin. And then, 28 degrees Celsius, 301. Okay, so let's do some math here. I'm going to do 82.6 times 31.2 and get this. 8.31 times 301, 2501.31 times N. Divide both sides by this quantity. Then we'll deal with sig figs in a minute. 2577.12 divided by 2501.31. Whoops, something happened. 2577.3. No, I'm getting there. 1.030308, blah, blah, blah. So let's take a look at our sig figs. So we have 3 here. This should really go to the tenths. So just go with it. And by the way, we had ended up with 3 sig figs here anyways. So 3 sig figs seems to be what we want. So this would become 1.03. Now, what are our units? Our units are moles. That's it. So this formula is not hard, although it's not in the regions. It's not that hard. I don't get it. So I think the only tricky part is figuring out which version of R to use, and that has to do with the units of pressure. Okay, thanks.